Okay, this is a video on inverse functions. So the definition of an inverse function is when you composite it with the function, you end up with x. So it undoes what f does. F of inverse f, so inverse f is notated as f to the minus 1 of x. F of inverse f will always be x. Inverse f of f will usually be x, but there will be some exceptions to that. And we'll have a look at those in a little bit. And this situation, if you have two functions that you composite together and it comes out to be x, then if you swap those round, that will also be x. And it means that f and g are both inverses of each other. So if you ever have a question that comes out with this, then you know that g is the inverse of f and f is the inverse of g. Okay. So how do we find the inverse function? Well, I have a few examples. The first couple are fairly straightforward ones, and then we're going to have a look at some where we need to restrict the domain. So here we have an f of x and an x. So if we want to undo what f does, then we want these to swap places. Is essentially what's going to happen. So whenever there's an f of x, you change it for an x. And whenever there's an x, you change it for, I would say an f of x, but actually I'm going to say f to the minus 1 of x, because in the process of swapping these two, you're actually stating the inverse. And now to get the inverse function, we just try and make that the subject of this equation. So I'm going to first divide by 3. So I get x on 3 is equal to the natural log of inverse f of x plus 2. I'm going to raise both sides to the power of e to get rid of my log. So that's going to be e to the x on 3 is equal to f to the minus 1 of x plus 2. And then subtract 2 from both sides will give me my inverse function, e to the x on 3 minus 2. Okay, and that's my inverse. The second example, I've drawn the graph of this one. And it's a good habit to draw the graph in. I should draw the graph of the previous one, but it was a one-to-one function. Feel free to check that out for yourselves. But yeah, I do recommend you always draw the graph of the functions because then that will allow you to decide if it is one-to-one. If it is, then fine, crack on. If it's not, then we need to restrict the domain. So this function here, f of x, is x plus 1 over x minus 2. Here's a sketch of that. So we can see when x is 2, the bottom of the fraction is 0. So that's going to give us a vertical asymptote. As x tends to infinity or negative infinity, these constants will become negligible in comparison. So we end up with x on x, which comes out to be 1. So it tends to 1 as x tends to positive or negative infinity. It crosses the x-axis when f is 0. That's when the top of the fraction is 0, as long as the bottom isn't 0 as well. Top of the fraction is 0 when x is minus 1. And for the y-axis, we set x to 0. So that's going to be 1 over minus 2, so minus a half. And this is the graph of y equals f of x. Okay, so that's my graph. We can see that this one is also a one-to-one function. Okay, for each x value, there is a unique y value, and for each y value, there's a unique x value. There's not one y value which leads to multiple x values, as you would see in a many-to-one function, for example. Okay, each y value gives only one x value. The only exception to that is, of course, y is 1, where x is not defined, but that's fine. As long as it's not more than 1, it's a one-to-one function. So because it's one-to-one, we can just take our x and our f of x and swap them over, just as we did before, and then rearrange. So this is going to give us x is equal to inverse f plus 1 over inverse f minus 2. And the reason I've chosen this example is because I'll now have two inverse f's here kicking around, so I need to deal with that. So it shows the algebra of this. Multiply both sides by the denominator of the right-hand side. Multiply out the brackets. Put everything with an inverse on the left and everything without on the right. Factorise out the inverse. And that's the key to getting two terms down to one, is factorising. And then finally, divide by the junk we don't want. We end up with inverse f is equal to 1 plus 2x divided by x minus 1. That's the answer. And you can check your answer by calculating f of minus 1, that should come out to be x, or indeed f of minus 1 of f, which will also come out to be x. So let's move on to a couple of questions which have a many-to-one feature on them. So this is a parabola. All parabolas are many-to-one. Graphs, you have many x values to one y value, which is fine as a function itself, but when we come to inverse it, we'll end up with a one-to-many mapping. One-to-many is not a function, so it would end up being a mapping. So the inverse function wouldn't exist. So what we're going to do is quickly sketch this to see exactly what is going on. So a quick check of the discriminant gives me 16 minus 20, that's minus 4. Square root of minus 4 isn't real, so it does not cross the x-axis. So I'm looking to complete the square. And if I complete the square on this, I'll get x minus 2 all squared. Okay, so half the coefficient of x. And then that's going to give me a plus 4 there, but I want plus 5, so I need to correct that with a plus 1. Okay, so that's what my completed square form looks like. And that tells me that this parabola has a turning point when x is 2 and y is 1. And I already know it crosses the x-axis at 5. It's a positive parabola, so it's going to look like a U shape. And this point here is 2 on the x, 1 on the y, and a really bad scale, but that's fine. That's 5 on the y, x, and y. For sketches, it doesn't matter too much about the scale as long as you get the feature of the shape and the intercepts correct. Okay, so that's what the graph looks like. We can see it's many to one because there are many x values that go to a single y value, which causes us issues. So the way we overcome this is we restrict the domain. So we restrict the domain. So instead of saying that x can be any real number, we say that x is actually only a certain portion of that, such that it will be a one-to-one function. And that's what we need to get. We need to get to a one-to-one function so that we can inverse it. I've chosen to take this part because then that maximises how much output we get, so how much y we get, without it being one-to-one, without it being many-to-one, sorry. So the domain, therefore, is restricted to x is greater than or equal to 2. Okay, so I've restricted the domain. And now that the domain is restricted, this means that... Sorry, excuse me. This means it's now a one-to-one and we can find the inverse. So just as before, we take the f and we take the x and we swap them over. So in this case, we're going to get x is equal to f to the minus 1 of x squared. Don't write f to the minus 2 of x, that's not correct. Minus 4 f to the minus 1 of x plus 5. Complete the square on that. Okay, when I make x a subject, so you've got to complete the square. Or you could use quadratic formula, I guess. So that's going to be f to the minus 1 of x minus 2 squared plus 1, which of course is the same as that, but with f to the minus 1 instead of x. Subtract the 1, so I'm going to get the square root of x minus 1 is equal to f to the minus 1 of x minus 2. Okay, so I've taken the minus 1 over, and I've square rooted this. And algebraically, I would have to consider both the positive and the negative square root. But in doing so, that would, of course, make it a one-to-many. And actually, because we've only taken x is greater than or equal to 2, then that says that we only need the positive square root. And now if we add the 2, we'll end up with f to the minus 1 of x as our subject. So it's the square root of x minus 1 plus 2. So the graph of that would look something like this. Just kind of stops at that point. This would be 1, and this would be 2. You can't sub in anything less than 1 into this, because then you'll be trying to square root a negative number. And the minimum this can be is 2, because this is always 0 or positive. When it's 0, the whole thing is 2. And you'll notice that the domain has swapped with the range. And that is common. That is, in fact, always true with inverse functions. So here, the range is f to the minus 1 of x is greater than or equal to 2, and the domain is x is greater than or equal to 1. Whereas back here, we had the range, f of x, was greater than or equal to 1, and the domain was restricted to be x greater than or equal to 2. So the domain and the range have swapped places in the inverse function. Okay, that's a feature of inverses. Okay, so note the domain and range swap places. There's also something else which I need to pick up on. In doing this process, it actually does something geometrically, and what is happening is it's reflecting the whole thing in the line y equals x. So as a geometrical implication of this, it's a reflection in y equals x. And again, that is true for all inverse functions. So you can see this curve here has been reflected in the line y equals x to give this curve here. Two more examples then. We'll do these together. So these are the trig functions. So we've got sine and cos. So both of these functions are many to 1. The reason why they're both many to 1 is because you have many x values which goes to the same y value. So what we're going to do is we're going to restrict the domain. So take the cos function. Okay, that's this graph here. And if I restrict the domain to be here, like that, then that graph is now 1 to 1. It still has the full range. Okay, it still goes from minus 1 to 1. But the domain's been restricted to be between 0 and 180. Okay, working in degrees. Pi if you're working in radians. Same principle. Okay, so we're going to take this function, we're going to restrict the domain, and now that it's a 1 to 1, we can inverse it. So we get then that f to the minus 1 of x is equal to arc cos of x. And the graph of that, again, as I said before, is reflection in the line y equals x. So it's going to start here, up like that, and then finish up here. 1 there, minus 1 there, and 180 up there on the y-axis. And that's the graph of arc cos. That's the entire graph. It doesn't continue. It stops at that point there, and it stops at that point there. That is the entire graph. And we can see that the range of this is between 0 and 180, and the domain is between -1 and 1. So again, the domain and the range have swapped places. Similarly for inverse sine, just use G because F is already taken on the page. That's going to be arc sine of x. But for this one, we can't restrict it between 0 and 180 because that would still be a many to one function, and also wouldn't optimize the range because it only goes between 0 and 1. So we actually take this little bit instead. So it goes between -90 and 90. The range is still maximized, so it's still between -1 and 1, but this time the domain is between -90 and 90. And again, we can draw a little graph of what's going on here. And it ends up looking something like that. Again, that's the entire graph. It just stops there, it just stops there. That there is -90. That there is +90. That there is -1. And that there is +1. It explains why your calculator will only give answers between -90 and 90 for the arc sine function, and between 0 and 180 for the arc cos function. It also explains why you cannot put an x value of less than -1 or greater than 1 into these functions, because it just doesn't exist at those points. Just to summarise then the domain and the range. So the domain of cos was between 0 and 180, and the range was between -1. I'll put y there, and 1, and the domain of sine was between -90 and 90. The inverse function, inverse of cos, was arc cos. Oops, you need 2 C's there. There we go. And the inverse of sine was arc sine. On your calculator, it's sine and cos to the -1, but I don't like that. The domain of the arc cos was between -1 and 1. Oops, that's next. Okay, so what was the range is now the domain, and now what was the domain is now the range. So it's between 0 and 180, and that's between -90 and 90. Of course, if you were asked to state the domain of sine itself, the domain is actually any x. So we'd say x is an element of the real numbers. Same is true for cos, but we had to restrict the domain to enable us to find the inverses. So I should really put restricted domain, because the domain of those two is x is any real number. Thanks for watching.